Okay, so we've got these energy levels and we've got the sublevels and the orbitals. And so how do we know where the electrons actually go? And so luckily there's kind of 3 helpful rules that guide us. Now, there's always exceptions to the rules, but this helps us have a general idea of how to fill in the electrons. We will do something called electron configurations here in just a little bit, but for now we're just going to focus on what's called an orbital diagram that just shows where those electrons are going to be. Okay, so the big 3 rules that we're looking at, one is called the Pauli exclusion principle, the second's called the off-bow, which is totally spelled incorrectly here, A-A-U-F-B-A-U. I'll fix that for your version of the notes. And then down there at the bottom of your notes, we have something called Hund's rule. So let's just go over these real quickly here. The Pauli exclusion principle basically says that no 2 electrons are going to have the exact same address, okay? You can kind of think of these rules as giving the address for an electron. You and your neighbor don't have the exact same address. You live in the same city, you live in the same state, you live on the same street, but you don't have the same house number. Even people that have the same house number, like if you lived in a duplex, one of you is maybe house A and one is house B. That's the same thing for electrons. So even if electrons are in the same orbital, they must have what's called spins that are opposite. So opposite spins. Now, really brief overview of what an electron spin is. So basically, when electrons or electron current happens, and it's a moving electric current, you get a magnetic field being produced. Okay, so here's a magnet, like a true bar magnet. And anytime you have a magnet, you get what's called a field line that goes around that magnet from one pole to the other. And the direction of that field line is very specific based on the direction of the magnet. Well, for your electrons, because they are spinning, they produce their own field lines. So here's going to be my electron. Kind of imagine it spinning around that particular axis that I drew there. And if this one was spinning this way, we could say maybe that its field lines would go, this way, okay, from top to bottom there. Whereas the other atom, the other electron in that same orbital would have to have an opposite spin. It would have to be spinning the other direction, and we could note that by noting that it would have opposite field lines. It would have to go, oh, that's the wrong thing. It would go from this way, top to bottom this time, instead of bottom to top. Okay, probably more than you need to know there. Just realize that when we draw them in our orbital diagrams, we will draw them with opposite facing arrows. That's representing the opposite spins, because no 2 electrons can have the exact same address in an atom. Okay, next principle is the off-bow principle. This is that electrons are going to go to the lowest energy state available. This is just how nature goes, right? Things tend toward the lowest possible energy state. And so here we have kind of just a little guide to help you know what that order is, because it's not always the easiest. Like it starts out, the first energy level just has the s orbital. The second energy level just has the s orbital, and then you go up to the 2p orbital. That's okay, so I just lied. The second energy has the s and the p orbitals, and then we go to 3, and then 3p and 4s, and you just kind of keep following it like this. You don't need to memorize this, okay? For now, I will give you a copy of it if you need it. Later, I'm going to show you kind of a more useful way to figure out what is the order that all of these orbitals fill. Okay, so we've taken care of this, we've taken care of that. Let's look here. Oh, I forgot to fill this one in. This is going back over to the Pauli exclusion principle. The opposite spin of the 2 electron forms a magnetic field within the orbital. Okay, that's super important to me, but that's how we know that they have opposite spins. Okay, each electron, as we know, can hold 2 electrons with opposite spins, and these are represented by an up half arrow. I didn't remember that I had these in the notes, obviously, because I already told you this. And then the other one is a down. We do just use half of an arrow. I don't really know why, to be honest. It's just kind of what we do. So an up half arrow and a down half arrow. So you can see that this is called orbital notation, and that's what we're going to be focusing on in this section. And then the last rule is Hund's rule, and this just says that occupies and electrons in the same energy level are going to fill in the empty ones first before they pair up, and then once they do, if they're not paired up, they're going to have the same spin. Whew, that was rough. Let me just kind of show you here. So like this would be the correct way to do it, and see, now I'm drawing with a highlighter. It's really, maybe I should give up for the day. if there's more than one available, so like a P sublevel, right? In the P, there's 3 different options available. We're going to want to put them in unpaired first. So they're not going to go on the same one, and then they're going to have the same spin. So this would be correct. This, filling in like those ones together, that would be incorrect. Okay, this is wrong, where our other one here is correct. So we're going to fill in all the up arrows first, and then we'll go back and pair it back up. Okay, so place 1 electron per orbital before pairing them, and then remember that these arrows represent our electrons with their different spins. Okay, we'll do a lot more examples of all these and try to get these rules all in our heads here.